Here we extend what we did in the last lesson on vectors. Last lesson we talked about what is a vector, how to calculate magnitude and direction, and then how to use head minus tail to bring things back to the origin, how to add two vectors. Now we're going to start talking about equal vectors. So because vectors have both magnitude and direction, if the vectors are equal vectors, then they must have equal magnitude and equal direction. We have a couple of options to show these things. To find the magnitude and show the magnitudes are the same, use the distance formula. For direction, you've got two options. You can either use an angle or show that the vectors have the same slope, and that would show that they're going in the same direction. Of course, you could also just bring them all back to the origin and show that they're the same vectors using head minus tail, so that's another option too. So here we have rule 1, rule 2, and rule 3. There we go. All right, so it says, show that vector u and vector v are equal to each other. So the first thing we can do is we can find the magnitudes. How do you find the magnitude of the vector? Well, for the first vector, vector u, the magnitude of vector u is the square root of a squared plus b squared, but what is a squared and what is b squared? Well, we've got to take the difference between -2 and -5. So where did it go? It went 3 units to the right, so I put my 3 squared. How about the y's? It went from 2 to 6, so it went 4 units up. So square root of 9 plus 16 is the square root of 25, which is 5. All right, let's do the same thing for vector v. This went from +2 to +5, so it went 3 units to the right. And then it went from 2 to 6, so it went 4 units up. We get the same thing. Square root of 25 is 5. So they have the same magnitude, but that doesn't guarantee they have the same direction, right? You can drive 5 miles to work and 5 miles to school, even though they're not in exactly the same place. So the vectors can have the same magnitude, but not the same direction. So let's then find the slope of the two vectors. Okay? Slope is change in y over change in x. So the slope of vector u is 6 minus 2 over -2 minus a -5. So 6 minus 2 is 4. -2 plus 5 is 3. So that slope is 4/3. The slope of vector v is going to be 6 minus 2 over 5 minus 2. So 6 minus 2 is 4. 5 minus 2 is 3. Equal slopes. All right, so they have equal slopes and equal lengths. The two vectors are equal to each other. The other option we had was to use the head minus tail rule and bring everything back to the origin, which is actually the shorter way of doing it. So using head minus tail, for vector u, we could take -2 minus a -5 for the first coordinate, 6 minus 2 for the second coordinate. And so if I brought it back to the origin, vector u would be 3, 4. All right, how about vector v? Do 5 minus 2, that's the difference of the x's. Do 6 minus 2, that's the difference of the y's. That gives me 3, 4. Look, they're the same vector, right? If I bring them back to the origin, they're the vector 3, 4 for both of them, so the two vectors are equal to each other. All right, I can also take vectors and I can multiply them. Multiply them by a constant. Constants we often talk about as scalars because it changes the scale as long as it's not 1. So it either changes the length of the vector or reverses its direction. When you multiply by a scalar, you multiply both the x and the y coordinates with a scalar. So my example here was if I take the vector 3, 5 and I multiply it by 3, sometimes we represent it like this, 3 times vector v. So 3 times vector v would be 3 times the vector 3, 5. So it would go 3 times as much in the x direction, 3 times as much in the y direction, which also means that it's now 3 times as long as the original vector. It still goes in the same direction, it's just 3 times as long. So scalar multiplication with a positive k value that's bigger than 1 makes the vector longer. You can see here what happens if I do it with other values. That first vector here is the original vector v. If I multiply it by a scalar of 2, it gets twice as long but still goes in the same direction. If I multiply it by something between 0 and 1, then it gets shorter, but still goes in the same direction. If you multiply it by a negative, it goes the other way. So look at that last vector that's multiplied by negative 3/2. It gets longer because it's multiplied by something with an absolute value that's bigger than 1, but because it's negative, it makes it go in the other direction. The other types of vectors that are sort of interesting to us are unit vectors. And unit vectors are vectors that are 1 unit long. Why is it interesting that I have a vector that's 1 unit long? Well, because basically unit vectors give us a direction. I can have multiple different vectors that go in the same direction that look very different, but if I reduce them to a unit vector, then I can show that they're all the same. Okay? Sometimes it's important for unit vectors also because I can use that direction to come up with information about other vectors. So we have two important unit vectors because they show up so often, we give them their own special designation. One of them is the unit vector that goes 1 unit along the x-axis. Okay, so it starts at the origin and it goes 1 unit that way. We call that I. It's the unit vector 1, 0. It goes 1 in the x direction, 0 in the y direction. The other unit vector that's important to us is the one that goes along the y-axis for 1 unit. And that's the unit vector that goes nothing in the x direction, but 1 in the y direction, and we call that j. So I is the unit vector that goes in the x-axis, j is the one that goes along the y-axis. Now that means we can write any vector as what we call a linear combination of I and j. So if you tell me that this vector 3, -4 goes 3 in the I direction, and then -4 in the j direction, that means it goes 3 units to the right and 4 units down. I can write it as an equation like this, or an expression, 3i minus 4j, and that's written as what they call a linear combination of I and j. All right, this I grabbed from the textbook. It gives you information about writing vectors from the origin to another point as A in the I direction and B in the j direction. So when you do that, you create what they call horizontal and vertical components. And I had mentioned, I think during the first video, that if you're traveling somewhere, like you're traveling that much in that direction, then you covered ground in more than one area. You didn't just go in that one particular direction. You covered ground 2 different ways. So you went a certain amount in this direction and a certain amount in that direction. So if this is east and that's north, then by going northeast, you went a certain amount towards the east, and then you went a certain amount towards the north. So this is the horizontal component, and that's the vertical component. And we can break those vectors down into their 2 separate components. And then the book, again, uses the word linear combination, so I write that in there like that. How do you find the magnitude of something written in ij form? The same way you do for a vector that's written in the standard form from the origin. Square root of a squared plus b squared, Pythagorean theorem. All right, this is another illustration of what I just put up there, that if you have a vector ab written as ai plus bj, that means that you went a certain amount in this direction, right? That's in the I direction, and a certain amount in the j direction. AI is a scalar multiple of I. So if it was the vector 3, 4, then you went 3 times in the I direction and 4 times in the j direction. The vector itself is the one in dark blue. That's the addition of AI and bj. Right? A units in the horizontal direction, b units in the vertical direction. All right, so let's try one that's written in ij form. It says, sketch the vector 3i minus 3j, find its magnitude. So what does this mean? That means we go 3 units in the I direction, and then the j direction is the y-axis, but it's going down. So this is my head. My tail is at the origin. There's my vector. It's got a horizontal and a vertical component. So its horizontal component is 3. The vertical component is -3. If I want its magnitude is the square root of a squared plus b squared. So 3 squared plus -3 squared. 3 squared is 9, so I get 9 plus 9. Square root of 18. And then 18 breaks down into 9 and 2. So 3 square root of 2. That's his magnitude. Or if you remember your 45, 45, 90 triangles from the beginning of the course, this is just a 45, 45, 90. If each of the sides are 3, hypotenuse is 3 square root of 2. All right, so it's nothing new conceptually, except that instead of writing the vector as 3, negative 3, we're now writing it in ij form. So we're writing it as an equation. All right, it's if you want to see what the book did when they, ooh, look, my drawing is right on top there. All right, so if you have 2 points, you can take those 2 points and turn them into a vector in ij form. And again, we already did this with the head minus tail rule. All this is head minus tail with some different notation applied. So let's take a look at an example to see how this works. So I've given you a vector. Right? Let v be the vector from point negative 1, 3 to point 2, 7. Write the vector in terms of I and j. All right, so we can make ourselves a little sketch. Notice that what was given are not vectors, they're points. So negative 1, 3 is up there. 2, 7 is up there. And the other thing it says is it's going from one point to another point. So it's going from P1 to P2. That's going to make a difference because if it went from P2 to P1, then I'd have to draw the arrow going in the other way. But it's not. It's going from P1 to P2, so that's the direction. So I need to take the points on P2 and subtract P1. So on P2 are the points 2, or the order pair 2, 7. 1 is negative 1, 3. So now subtract them. 2 minus a negative 1 is the first coordinate. 7 minus 3 is the second coordinate. So 2 minus a negative 1 is 3. 7 minus 3 is 4. But look, the question said to write the answer in terms of I and j. So in terms of I and j, it's positive 3 in the I direction and positive 4 in the j direction. So now my vector is 3, 4, but the question said to write it in terms of I and j. So I have followed directions and I've written it in terms of I and j. What it's saying is that from the first point to the second point, you would get there by going 3 units to the right and 4 units up. 3 is the horizontal component, 4 is the vertical component. And this picture illustrates that I can take that vector up here, right, from negative 1, 3 to 2, 7, and I can use head minus tail to bring it back to the origin. And so there it is as a vector back at the origin that's going 3 units to the right and 4 units up. All right, let's take a look at this. Adding and subtracting vectors. We'll get into a little bit of scalar multiplication also. So it says, given vector v, given vector w, add v plus w. Well, what do? We take the first components. The first components are 7 and 4. So those are both the ones that go with the i's. So let's combine the ones that go with the i's together. And now let's combine the ones that go with the j's together. So I get 3 and I get negative 5. And now simplify. 7 plus 4 is 11. So 11i minus 2j. And that's it, right? It's an a plus bi form. You can add vectors together and get them as 11, negative 2 also, unless it specifies that it has to be written one way. The second one says do v minus w. So now we're going to take all the components and subtract them, meaning we're going to do 7 minus 4 in the I direction, and we're going to do 3 minus a negative 5 in the j direction. We still put the plus in between them, right? Because it's ai plus bj. So we're still putting that plus in between to show that it's a linear combination of i's and j's. It's the individual components that are now subtracted instead of added. So 7 minus 4 is 3. 3 minus a negative 5. Right, what about problems that involve scalar multiplication? All right, for scalar multiplication, it really is as easy as multiplying by the scalar. So this vector here was given as 7i plus 10j. I might just rewrite it like that. All right, 7, 10. So now it says multiply that vector by 8. So when I multiply that vector by 8, 8 times 7 is 56. 8 times 10 is 80. So I can represent it like that, or I could represent it as 8 times 7i plus 10j. and just multiply each of those components by 8. So 8 times 7 is 56. 8 times 10 is 80. All right, how about negative 5 times the vector? So negative 5 times the vector is going to be negative 5 times 7i plus 10j. And negative 5 times 7 is negative 35. Negative 5 times 10 is negative 50. So I could represent it as negative 35i minus 50j. Or I could represent it in this form also, negative 35, negative 50. So the vector has gotten longer, but it's also flipped, and now it goes in the other direction. Right, the other thing that happens every once in a while is you come up with what we call a zero vector. So a zero vector has no direction, and it really is a vector that is of zero length that sits at the origin. There are applications for the zero vector, and we'll maybe get to them a little bit later here or in future courses. But if you have a zero, and you can represent the zero vector, by the way, by writing a 0 and putting a little vector on top of it. What that indicates is that that's not the number 0, that's the zero vector. So since we're in 2 dimensions, the zero vector is the vector 0, 0, or you can express it like this. Now you notice I got this from the textbook. They put their 0 in bold. This pen, I guess this pen actually has a bold if I could figure out how to put it on the computer, but let's just call it like this for now. 0 in the I direction plus 0 in the j direction. Right? And that's the zero vector. All right, we'll stop this. We'll do one more with this section that's got unit vectors and applications in it.